Okay, thank you very much. My name is Jin-Sung Kim. I'm part of the quantum computing team at NVIDIA. I'll be very happy to tell you about some of the work that we've been doing over the past several years in the quantum space, and really the work that we've been doing with the entire quantum ecosystem. So really to motivate some of the work that we've been doing recently, it's really instructive to look at some of the great work that's been happening in the quantum field in the past year. So it's been a really amazing year of breakthroughs in kind of two broad buckets. The first being quantum error correction with some very, very nice, real tangible results in the field of quantum error correction by the likes of Google, Quera, Quantinuum, and Inflection. And then kind of the second broad bucket of very nice results in the past year are those in novel quantum architectures. So quantum hardware that has the potential to really drastically reduce the overheads of quantum error correction. So architectures from Microsoft, AWS, as Oscar Painter talked about in the keynote yesterday, as well as some novel architectures from PsiQuantum and Xanadu that are kind of inherently scalable and can nominally be scaled out to an entire data center. So what we really love to see here at NVIDIA is that there's so many different modalities with serious efforts and progress being made in the field. We are very optimistic about quantum computing as a novel way of accelerating some of the world's most important problems. We've been working on quantum computing for several years now, and so we're excited to see where the future takes us. So how does NVIDIA fit into all of this? Well, we are not building our own quantum computer or our own qubits. But what we are very good at and have a lot of expertise in is building heterogeneous compute systems using new types of accelerators, networking them together, scaling them out, and ultimately making them into useful scientific tools. So we did a very good job with this with the CPU and the GPU, and we're going to now include the quantum processor in this. So what we think this will look like in the future will be a quantum computer of various modalities next to a supercomputer. And as we all know, quantum computers will not do everything themselves, but will be a critical part in solving some of the world's most important problems that we can't solve today. But on the flip side, GPU supercomputers are very useful tools in making advancements in quantum computing today, and we think will be a very important part of useful workloads with quantum computers in the future. So we really have to carefully consider what a fully integrated system looks like, from the low-level systems integration to the high-level methods for applications. And so for us, what our platform this vision is our North Star. This is our vision called the Accelerated Quantum Supercomputer. This is what we're trying to help the entire ecosystem build towards. So this is connecting QPUs of all architectures to AI supercomputers. Our CEO, Jensen, at his latest keynote, mentioned that he predicted that all supercomputers in the future will have a quantum processor next to them. And so we're building a platform that enables everyone to be able to do this and leverage supercomputing alongside quantum computing. So this is really important for a couple of different reasons. We want to be able to develop hybrid applications, so fully utilizing AI supercomputing, HPC, and AI alongside quantum computing. Developing the low-level and low-latency connections between the quantum processor and the GPU. So some very nice comments from Jonathan about the work that we've done with quantum machines on developing very low-latency connections from the quantum processor to GPU systems themselves. And then all the way up to the high-level libraries for enabling the end user and domain scientists to program a quantum processor in the same way that they would program just a normal computer. So CUDA-Q is our software platform and programming model for quantum computing. It's open source and qubit agnostic. So if you're familiar with CUDA, which is the framework that has allowed the massive scale out of GPU and the entire associated ecosystem, CUDA-Q is our framework for programming a quantum processor in a similar way. So integrating them into supercomputing scale GPU systems and ultimately helping make quantum computing useful. So a big part of this is the enablement and the integration with the entire ecosystem. So we're a platform company, and our success is driven by the success of our partners. So on this slide, you can see all of the companies that we've integrated with so far. These are quantum hardware companies that are developing their own qubits. There's a number of others who are also integrating as we speak. But what you'll notice here is there's qubit modalities represented across the entire spectrum of architecture. So from superconducting qubits, photonics, trapped ions, neutral atoms, spin qubits, the whole gamut of architectures. So in addition to quantum hardware integrations, we've also developed a set of very powerful simulation tools for quantum. So simulation for us is very complementary to quantum computing. We don't see it as a competitive tool by any means, but instead it's a very useful tool for developing new applications and understanding kind of the scaling behavior of novel applications. So it's a very powerful tool for developing new quantum applications and really understanding where the advantages may lie. In addition to this, it's also very useful to be able to model noise. With all of these quantum frameworks we have integrations with, you can still write applications in your favorite quantum frameworks, whether it's Cirq or PennyLane or Qiskit or Kibo. You can accelerate all of these simulation frameworks with our cuQuantum libraries. We have integrations with all of these frameworks today. So one thing that's really important for us to highlight here is that we build out an entire platform, but we also distribute it in a disaggregated way. So if you want to write applications in CUDA-Q, you can do that. But if the right integration point for you is another quantum framework, you're perfectly welcome to do that as well, and we can still give you the acceleration that will accelerate your workloads. So on the opposite ends of the stack, we now have a new set of libraries called CUDA-QX. So these are high-level libraries for accelerating applications development. The first one is called CUDA-Q QIC. And so this is really a library for enabling the development of quantum error correction codes and leveraging the GPU to accelerate things like code discovery and decoding. I'll talk a little bit more about this in a few slides. The second one is called CUDA-Q solvers, and this is a set of APIs for developing things like quantum chemistry and material science applications. At the very bottom of the stack, we have a system and reference architecture called TGX Quantum. This was done in collaboration with Quantum Machines. So this is a system, as Jonathan mentioned, that enables a very low latency connection from a very powerful GPU system, which can be scaled out to supercomputing scale, and the OPX system. So we're seeing less than 4 microseconds latency communication between the GPU and the quantum controller. So this is our platform. It's open source and available to use. We build the whole platform, but we distribute it in a disaggregated way. So our partners can either take the whole stack if it's useful for them, or they can just pick and choose the parts of it that are most useful to them. So as I mentioned before, we're a platform company, and our success is dictated by the success of our partners. So when our partners succeed, we succeed. And so we're really happy and proud to be able to partner across the entire quantum ecosystem. It's a true privilege to be in a position where we can really partner with every person and organization that's working on quantum computing. So this is from early stage startups to some of the largest companies in the world. So how do we get to where we are today, to where we want to be in the future, to realize a fully fault-tolerant and accelerated quantum supercomputer? So very broadly, from our perspective, the 3 biggest challenges here are we need to build better and higher-performing quantum hardware. We need to develop and design better algorithms and applications to really identify what the useful workloads and the world-changing workloads might be with a quantum computer. And in order to be able to actually implement those, we need to be able to scale quantum error correction. So we've built a platform that we think is going to help with each one of these. So starting with better quantum hardware, we of course need better qubits with longer coherence times and better gate fidelities. And so a lot of this work is very deep engineering and material science work, but at the same time, simulation is a very powerful and useful tool that can help design better quantum hardware. And so one of the collaborations that we announced last year was towards this end. This was a collaboration with the Google Quantum AI team, where we developed a simulation library for extremely performant quantum dynamic simulations. So this is actually simulating the evolution of a quantum system in time and seeing how it interacts with the environment. So as I'm sure everyone here knows, one of the biggest issues in quantum hardware is how to deal with and mitigate noise. So things like coherence continue to get better every year, and there's been enormous strides in the material science and engineering to improve the performance. But understanding the sources of decoherence and ultimately the interactions with other quantum objects in your system is really fundamental to understanding how to mitigate these noise sources. So having a powerful way of simulating qubit dynamics and their interactions with the environment is actually a very useful way of mitigating errors in hardware and designing better hardware in the future. So in this case, I'm talking about the evolution of open quantum systems as opposed to circuit simulations. So instead of thinking about logical or noisy qubits, we can take a bit of a closer look at the actual quantum device and treat them as arbitrary quantum objects that are not just restricted to 2 levels. We can consider their full interactions with each other. We can consider their interactions with stray fields in the system. And ultimately, we can controllably do these types of simulations and ultimately iteratively improve the cycle time that it takes to actually build and design new quantum hardware. So instead of having this very long cycle time to design a new device and then cooling it down and then measuring it experimentally, hopefully what we can do is actually just simulate many of the processes here a priori and then design a better quantum system from the get-go. So dynamic simulations, very similar to other quantum simulation methods, is very computationally expensive, but there's a lot of optimizations that can be had, and these types of simulations actually run very nicely on GPUs. So what I'm showing here is a benchmark of simulating a superconducting qubit, a transmon, and we can actually couple it to a couple of different other electronic elements in the system. So for example, we're coupling it to a resonator and a Purcell filter. And we're simulating 64 levels of the qubit, 256 levels of a resonator, and 4 levels of the filter. And using kind of a popular CPU-based dynamics framework, Qiskit Dynamics, if we just simulate one time step of the system, it takes about 44 minutes. So this is a very difficult system to examine and pretty prohibitive to actually run in a study. But with CUDA-Q Dynamics and DGX H100, we're able to get this down to less than a second. So that's about a 10,000x speed up for a single time step, both from benefits from the hardware and the software optimizations. But really, this is the impact of this is that this is taking a workflow that is basically impossible to look at, or it takes all day to look at. And now this brings it down to a time scale where it becomes a reasonable workload to look at. So this functionality has been released in CUDA-Q as full solvers. So you can just define your Hamiltonian and your time schedule, and then with a single line call, you can do the simulation. But we also released the building blocks of these simulators. So frameworks like Qiskit Dynamics can also pick up these acceleration APIs and also accelerate their workloads. So once again, we build a full stack, but we distribute it in a disaggregated way so that our partners and other frameworks can also pick up our simulation capabilities and accelerate their workflows. OK, so let me switch gears a little bit and talk about some of the work that we've been doing in the algorithms and applications space. So this is a major research topic among folks in the field. So I'll just focus on a couple of recent examples that we've been involved in. So the first example here is work done with IonQ, AWS, and AstraZeneca. This is a quantum chemistry workflow using auxiliary field quantum Monte Carlo. So the quantum part was run on the IonQ Forte device, and then a massive amount of post-processing has to be done on GPUs to actually formulate a sensible answer. So this leveraged about 1,000 GPUs on the back end for the post-processing. You have to do these wave function overlaps, which are extremely computationally expensive. But overall, for this workflow, the overall time to execution was about 20 times faster for an end-to-end speedup. So this is a really nice example of a truly hybrid application where part of the workload is run on a quantum device, and then part of the workload is run on a GPU system. And this is towards a workload for drug discovery. The second example of work done in collaboration with the quantum team at HPE. So one of their main research interests, similar to us, is thinking about what a distributed quantum computing system will look like in the future. So it may be the case that a useful quantum computer has to have many different quantum nodes. And so we're starting to think about what are some of the workloads that we can run to extend the functionality of such a system. And one such example of these workloads is something called circuit knitting. So this is strategically dividing up a quantum circuit into smaller subcircuits and then running each one of those circuits on a quantum node and then classically stitching those results back together. So this process can be exponentially expensive in the classical post-processing. But as it turns out, if you're very strategic about where you make your cuts in your circuit, you can drastically bring down this overhead. So what the HPE team has done is developed an adaptive circuit knitting technique that can actually drastically reduce the sampling overhead required for this, oftentimes by a couple of orders of magnitude. So very interesting work to couple multiple quantum nodes together and see what kind of interesting workloads that we can do. The final example that I'll show is recent work from the NCHC team in Taiwan. So what they're looking at here is the scaling behavior of quantum machine learning workloads. So very notably, they're using our tensor network library. So there's methods of simulating very large circuits, albeit shallow, using tensor networks. And this is a very interesting way of understanding the scaling behavior of pretty large quantum systems. So in this paper, they looked at about 800 qubits for this quantum machine learning, this quantum support vector machine. But more recently, they've expanded this to a 4,400 qubit simulation, leveraging our tensor network backend. So really nice work to understand kind of the scaling behaviors of these types of workloads. OK, so the last thing that I'll talk about is some of the work that we've been doing in quantum error correction. And so this is really one of the key ingredients that we need to tackle to achieve some sort of quantum advantage in the future. So if we just look at some of the state-of-the-art gate fidelities today, we're seeing about 10 to the minus 3 error rates for 2-qubit gates, which is very, very nice. But what we expect to need for a useful quantum application in the future are error rates more on the order of 10 to the minus 10. So the way that we get to this level of accuracy is by leveraging quantum error correction. And so very typically, what this sequence looks like is you do some sort of syndrome extraction from your quantum processor, or you probe some measurement qubits on your quantum processor, and then you have to figure out what errors have occurred on your system. This is the process known as decoding, and then you have to resubmit the corrections back to your quantum processor. So in practice, most of what's happening on a fully fault-tolerant quantum computer is actually just quantum error correction. So if we take some numbers from this Craig Gibney paper back from 2019, he's recently published a new paper with updated numbers for this Shor's algorithm. But basically what you see is there's about 14,000 qubits necessary to run Shor's algorithm for a useful workload. But ultimately, the physical number of qubits that you need is order 1 million, or 20 million in that older example, but 1 million in this his newer paper. And so you can see that most of what's happening on a quantum computer is just the quantum error correction. So it's mostly just doing these quantum error correction cycles with a little bit of actual compute. So all that to say is that this is a very difficult classical compute problem that we have to tackle. So when we're thinking about the classical compute side of quantum error correction, there's kind of two axes that are the most important. There's the code distance. This is how much error that you can suppress at the expense of more qubits. And there's also the decoding time. So this is how long it takes to figure out what error has occurred on your system. And for practical quantum computing, you really want to be on the bottom right-hand side of this plot. So high code distances with a small decoding time. And as it turns out, this is a pretty difficult problem to tackle. So typically, your decoding time using industry standard decoders scales something like a polynomial. So one thing that we can do is just parallelize. And this is a pretty good strategy that runs pretty well on GPUs. But then the other strategy that we've investigated is leveraging AI methods for decoding. So I'll first talk about our parallelization efforts. So we recently released a new GPU-accelerated BP-OSD decoder, which is a very popular decoder for so-called QLDPC codes, which is a very popular method of doing error correction today. And to our knowledge, this is the first GPU-accelerated decoder publicly available. We're getting about 30x speed up over industry standards using our new BP-OSD decoder. And then the other thing that you can look at is the overall throughput of this decoder. So given multiple syndrome measurements at the same time, we can just batch these together and then get an additional something like 40x speed up for batch decoding. So really nice, very promising start to accelerating the real-time decoding process for some interesting quantum error correction workloads. The second method that I want to talk about is our work in collaboration with QIRI on AI methods for error correction and decoding. So there's a pretty exciting and promising reason why we would want to use AI for these types of problems. And the reason for that is that you can front load all of the computation to training a model, and then running inference for your decoding can actually be relatively scalable and relatively fast. So you don't have to do the brute force computation of your decoding in real time as you're trying to do the decoding, but instead you can make an effort to pre-train the model and then do that beforehand, and hopefully have a much scalable method of running decoding. So that's the hope. So we built a transformer model decoder in collaboration with Quora. We used a model that was trained with synthetic data with some realistic noise from the quantum processor and got some really nice preliminary results for a small system, just a d=3 code. But we were able to get better results than their previous decoder, which was based off of most likely error. But the really interesting thing is that the decoding time here was about 50 times faster than the previous state of the art. So really starting to get into the regime of being able to do real-time decoding using AI methods. And so state-of-the-art performance and also accuracy. So hopefully the thought here is that we'll be able to scale this to larger systems and push on the results of this AI method. So there's a lot of work that needs to be done to actually make this useful and scalable. And so there's a couple of challenges here. For larger code, we need much more training data. We'll really need to fine-tune the model on a quantum processor for higher accuracy. And then there's challenges in deploying this for real-time decoding. So getting the latencies down for actually doing this on a real quantum system. But we've made some really nice progress towards the first one of these, at least, to generate a massive amount of synthetic data for using custom noise models. So what we've done is built this pipeline that allows you to take a custom noise model, generate a massive amount of synthetic data, and then leveraging DGX H100 supercomputer, we were able to use our tensor network backend to generate 1 million shots in about 6 hours for an 85-qubit system, and also a 35-qubit system, a trillion shots generating about 2 hours. So this is released open source. Our hope is that everyone can be able to leverage these tools to generate their own data sets. This is really a tool to enable the entire ecosystem to generate these large-scale data sets to train these types of AI models. One last thing that I should mention, we leverage this open source PhysicsNeMo AI physics framework. That's also another NVIDIA product. OK, so one of the last things I want to talk about is this DGX Quantum Alpha release. So this is done in collaboration with Quantum Machines. Just want to mention that the first ones of these systems have been shipped to alpha customers. So the first one's being Dirac, which is a spin qubit company based out of Australia, and then a group at MIT, Will Oliver's group, at the Engineering Quantum Systems group. And there's a number of other systems that will be going out that will be leveraging this very low latency system. So now, just zooming out, I do want to mention that this model of the accelerated quantum supercomputer is already starting to happen at supercomputing centers all around the world. So the ones here are already deploying quantum processors next to GPU supercomputers and are really starting to push the forefront of research within the intersection of supercomputing and quantum computing. And to that end, in March, we also announced that we are joining suit. So NVIDIA is doubling down on our efforts in quantum computing. And part of this effort is this new research center based in Boston called the NVAQC. The centerpiece here is a new Grace Blackwell 200 NVL72 supercomputer with more than 500 Blackwell GPUs. So the research thrust here will be large-scale simulation for algorithms and hardware development, training AI models for quantum computing and decoding, investigating the systems level integrations necessary for a tightly integrated accelerated quantum supercomputer. We're not doing this alone. We're doing this in partnership with quantum companies like Quantinuum, Quora, and Quantum Machines, as well as academic groups from Harvard and MIT. And we'll also be open sourcing a lot of this work so that the rest of the ecosystem can also benefit from it. And with that, I'd like to thank you for your time and take any questions.